Okay, let's continue with paper 42, February, March 2025. Question 6. An electric field and magnetic field are used to form a velocity selector. So that's your velocity selector. The charged particle called ions, that's your ions, pass into region of uniform electric and magnetic field. Uniform electric and magnetic field inside here. What is that is between the parallel plates as shown in figure 6.1. The potential difference between the plates of the velocity selector is V. The separation between the plate is D. That is D across the plate is V. And the magnetic flux density is B. Right? You are asked to show this equation for undeviated bin. Okay, so we just put magnetic force equals electric force. So magnetic force Q is the charge on the ion. Q and Q cancel off. Then we replace E with V over D. And U take our B down. Okay, positive ion of kinetic energy, that one there, mass that pass undeviated through the velocity selector, where V is equals to 980 volt. D is given, determine D. Right, that's the kinetic energy. Right, from there we can calculate our U. A lot of calculation in A2 lah. Cannot avoid it lah. Right? So take the 2 across there, take the M down, square root it to get U, and put in the value. Right? 2 energy 4.1 times 10 to the power minus 17. Mass, that's your mass. And use calculator, get the answer. And use the formula we just derived. D, take a U down. 980 volt. D, that's your D. That's your U. Okay, out. Two significant figure used to answer two significant figure. Okay. A proton pass undeviated through the vertical velocity selector. An alpha particle enters the velocity selector at the same speed as a photon. State how the expression in A predicts that the alpha particle also pass through undeviated through the velocity selector. Okay? You want to try without looking at your answer? Since you have done it. Can? Yep. Have a go.
This one,
Can?
I just wrote independent of mass and charge. Depends on
Basically, we are
speed.
just using this formula lah. So this formula is not dependent on mass and charge. The expression is independent of mass and charge. Must be there. Okay? Okay, by reference to figure 1.6, that's your figure. And the forces acting on the positive ion determine the direction of the magnetic field and explain your reasoning. Where should the magnetic field be?
Electric force downwards, magnetic force upwards.
Huh?
Current is from left to right.
Okay, electric force is downwards, so magnetic force must be upwards. Then we use Fleming's left-hand rule,
Into the
positive
page.
ion, so the current is from left to right. From Fleming's left-hand rule, magnetic field is into the page. It can be either in or out of the page only. So they use Fleming's left-hand rule to check. The positive ion enter the velocity selector with a greater kinetic energy. Sketch on figure 6.1, sketch the path of the ions. How should it go?
That's above should be going up.
How to reason it out? Magnetic force depends on velocity. Electric force doesn't depend on velocity. So if the greater kinetic energy, greater velocity, so greater magnetic force. So you're going upwards, right? Electric force is downwards. Okay, good. Then Faraday's law, it looks like this is becoming popular in electromagnetic induction. Used to come out every year, but since 222, they concentrate on Hall effect, magnetic field. Now they are coming back. Induced EMF is directly proportional to the rate of change in magnetic flux linkage. Metal rod, as a metal rod, is accelerated uniformly from rest in a uniform magnetic field as shown in figure 7.1. The rod has a length and magnetic flux density B, length L, that's the length. The electromotive force, is induced in the rod. The variation with time t of the induced EMF is shown in figure 10.2. Explain how figure 7.2 show that EMF is proportional to velocity. Right? Starting at rest, we are just going to our AS, V equals to U plus AT, U equals to 0, so V equals to AT. Uniform acceleration, A constant, V is directly proportional to time, right? E is proportional to time, so E is proportional to velocity. EMF is directly proportional to time, so E is proportional to V. Okay, can? Okay. Use Faraday's law to show that the variation of E with time is given by the equation BLAT, is acceleration of the rod. Right? That's the distance x travel. Right? V equals U plus AT, where U equals 0. That's Faraday's law. Rate of change in flux linkage divided by time. So it's BA. BA divided by time is T. B L times X divided by T. X over T is V. So V is AT. That's how we get a formula. The length of the rod is 0.45 meter. Acceleration A of the rod is 7.8 meter per second square. Determine the value B. Right? That is the equation. B is take the 2 downwards, LAT downwards there. And Right? Take any point, no? Easiest to take the end point, no? Easy to read. Right? There's your 0.03 millivolt change to SI unit. And the time is 2 L. L is 0.45 meter. Speed. That's your speed. Acceleration, sorry, 10.8. Okay, out. Okay. Anything need me to explain further?
Mm. So,
No, let's carry on. State what is meant by a photon. Okay, without looking at your answer, see whether you can remember. Can
photon is a
quantum of energy of
not sure.
electromagnetic,
Can you hear me?
very soft. Quantum of energy of electromagnetic radiation. No? Okay, memorize. Or packet, no? Packet of energy. Packet of energy of electromagnetic radiation. A laser emits straight light of wavelength of a single wavelength. The light is produced when electrons move from a higher energy level to a lower energy level. The difference in energy between the two levels is 1.96 electron volt. Calculate the wavelength of light. So
epsilon
use this
lambda.
formula.
E equals epsilon lambda.
This is higher energy level, this is lower energy level. HF, HF you replace it with HC or lambda. Right? That one is in joule. So take cross multiply. H is Planck's constant. C is the speed. That one is 1.96 electron volt. 1 electron volt is 1.6 and 10 to the power minus 19 joule. To calculate out 6.3 times 10 to the power minus 7 meter. Power of beam emitted by laser is given by that. Calculate the number of photons emitted per unit time by the laser. Right, that's the energy of the photon emitted. Lambda is that. Right? Or just use 1.96 times that. Calculate the energy emitted. Convert it to joule, 1.96 electron volt given. Then power equals to n number of photon divided by time times energy of the photon. And we want to calculate NT, take the E down, power, right? Power, E is this one there, calculate out. Can,
Mm.
okay, this one we have calculated. The photons are incident normally on the surface. Half of the photons are absorbed by the surface and half is reflected. Determine the average force exerted by the beam of photon on the surface. So this is your AS work plus A2 work. Calculate the photon energy, the momentum of the photon, right? Use de Broglie's formula, Planck's constant, wavelength. It's a wavelength that we have calculated earlier. Calculate the momentum. Half momentum have momentum P is absorbed, that's why we have P. The other half have momentum 2P is reflected, so it's got 2P. So instead of just using this formula, we have to consider 2p, then one is 1p lor. Then take the average of that lor. Can? Any comment or anything? Not.
No.
Polonium-193 is an unstable nuclide. The nucleus of polonium-193 decays to a nucleus of lead-189 by emitting alpha particle. Radioactive decay is both random and spontaneous. State what is meant by random. Okay, what is meant by random? Without looking at the answer,
Can happen at any time.
cannot predict when a particular nucleus will decay. Spontaneous,
Unaffected by external factors.
not affected by external or environmental factors. Define half-life. See, we can define
Uh, Time taken for the nucleus to decay to half.
time for activity to half lor. Okay, data from binding energy per nucleon, of particles involved in the decay of nucleus of polonium is given. Right? That one is a particle. This one is the binding energy per nucleon. Determine the energy in electron volt released when the nucleus of polonium decays into nucleus of lead. So this is energy of lead per nucleon times 189 lor. And then this is 7074 times 4 lor. And then this is polonium, the initial particle, 7.74 times 193 lor. 193 electron volt. Pure sample of polonium contains anode nuclei. After a time of T, the sample contains N nuclei of polonium-193. The variation in ln N over N naught and T is shown, right? It's ln N over N naught. It's your time. So go to the theory, go to the, right? We are lost. Go to the formula sheet. They have given you the formula. So replace the X with your N, right? Then write in this form, ln. So we can find the gradient from lambda from the gradient. State the name of the quantity that is represented by the magnitude of the gradient of the line. Yep.
The constant. Decay constant.
Okay, decay constant. Use figure 9.1 to determine the half-life in millisecond of polonium. So if determine the decay constant, that's why you say decay constant is a gradient. So ln that, right? Lambda is a gradient. So it's as I say, always take the easiest point to read. The last point. Then it's 1.4 divided by 0.84. Then you get 1.67. And then go to the formula sheet. If you can remember it so much, the better. You cannot go to formula sheet and calculate out. Can? Any comment?
No.
This is medical physics. Positron emission tomography, PET scan uses radioactive tracer. State what happens to the positron emitted by the tracer. Okay, you can remember? Yep.
Annihilate when collide with electrons.
Mm. Positron collide with electron and annihilate. Explain why a tracer with a half-life of about 2 hours is suitable tracer to use. Yep.
It's long enough to build image without
Long enough
yeah, I think
to
long
have
enough to
time
build
to
image.
conduct investigation, not so long to cause patient unnecessary
Oh
exposure
yeah,
to radiation. Right? We want to keep the patient safe.
radiation, yeah.
At the same time, when we expose him to radiation, we want as short a time as possible. So 2 hours is a short
So
time.
if just write long enough can lah.
Long enough, I don't think they will allow you lah. Long enough to have time to conduct investigation, not so long as to cause patient unnecessary exposure to radiation. Okay? Paper 4 is more demanding lah. They require you sometimes, they won't give you mark for working lah, but you need to do working to get the answer lah. Okay?
Yep.
State what is meant by luminosity of a star. Okay, see you can remember.
Power
Not power, total power.
of radiation emitted.
Right? Total power of radiation emitted by the star. Explain how standard candle are used to determine the, the distance to the galaxy. Yep.
Uh, by measuring the radiant flux intensity and using the formula.
First, the first point, standard candle has known luminosity. Right? This one is known. L is known. Measure the radiant flux intensity. Measure F. Measure L. Both are known. L is known. F is measured on Earth. Then we can calculate our D. Calculate D. Okay.
Yeah.
The sun rotates on its axis. X and Y and Z are the equator of the sun as shown in figure 10.1. The wavelength of light on points X and Y are observed and recorded in table. The sun rotates, a period is given. Show that the radius of the sun is that delta lambda over lambda. This one is given in the formula sheet. Okay, we just want this one and that one there. One V is that cross multiply, take the C across there, put in your value, the speed of light. That one is getting from a table there. So minus that. Okay, then divide by this one. Y is nearer to the earth. This one is rotating. X and Y, X and Z. 2103. And from there, right, velocity is 2 pi r, circumference divided by period, right? Distance divided by time. R is Vt divided by 2 pi. V is that one there. V period is given, period, and 2 pi. Can
Yeah.
then explain how the expected wavelength of light observed from Z compares to emitted wavelength. Yep. Z is moving towards the
When X moving away,
X.
so Z is moving towards Earth.
Yeah,
Hence,
X is moving
wavelength observed
away.
will be
So we are
less.
interested in Z. So Z is moving towards the Earth. So observed wavelength is less than the emitted wavelength. The luminosity of the sun is given. Use the information in B1 to calculate the surface temperature of the sun. Right? We have got the radius. Right? Use the luminosity formula from the formula sheet. Right? Take the others across there. Take the square root to the fourth power. L, that's a luminosity, 4 pi. Right? R, that square. Even constant can get from formula data sheet. Right? Two significant figure, so it's 5800 Kelvin. Okay, any query?
No.
Okay, I think we have completed. Let's go to the next paper. Okay, let's go to October, November 2025, paper 41. The next one will be 42 lah. Then after that, 44 lah. So we take 1 week off for Chinese New Year. In terms of velocity and acceleration, describe uniform circular motion of an object. Okay, see whether you can remember.
Let me open.
Velocity and acceleration both constant magnitude. Velocity is always perpendicular to acceleration. Remember that?
Vertical.
Got 10 more minutes. Figure 1.1 shows a view from above of polystyrene ball undergoing horizontal circular motion of radius r. Right? Basically, this one I stopped teaching now because never come out. This is the first time it come out. So this one is undergoing circular motion. The shadow on the screen is going to and fro lah, in harmonic motion lah. The ball is illuminated by a parallel light so that the shadow of the ball forms on the screen. That's the shadow. That's the beam of the light. Do the experiment in the dark room there. The line joining O and P is perpendicular to the screen. Okay, this one. This is the rest position now. The angular speed of the circular motion is omega. So circular motion is omega angular speed, whereas in simple harmonic motion is called angular frequency. It's the same. Omega. Say an expression in terms of R omega for the speed, memory work. Okay. Determine the expression in terms of V and omega, the centripetal acceleration of the ball. This one came out years ago. Right? A is V squared over R. I can use R omega squared. Then your R, we don't want R. Right? So R is V over omega. Replace your V and omega here. So you get your answer V omega. The ball in B is in position shown in figure 1.1 such that the line OB is an angle of theta to the line OP. Determine the expression in terms of R theta for the displacement x of the shadow. Right? So this distance, that distance there, right? That's your x, that's your R. So R sine omega t. That's all.
Okay.
You can use velocity also lah, but unnecessary extra work lah. Right? That is your tangent of the velocity going this way. There's angle theta there. This one is tangent 90 degrees. But this one is also theta. Unnecessary, no point in using this method. I can use that lah. Right? V equals V cos theta. Then replace it with x omega. And then R omega. Then omega cancel out. Right? Unnecessary lah, this step. Theta is 0 at time t equals 0. Theta equals 0 at time t equals 0. Take the expression in terms of theta, in terms of omega t, memory work lor. Theta is omega t. Use your answer in C part 1 and C part 2 to show that x is given by the equation. Right? That's the equation that we have obtained. Right? We have quoted. Then replace theta with omega t. Explain with reference to equation C part 3 why the motion of simple of the shadow of the ball on the screen may be modeled as simple harmonic motion. Right? Equation of this form is simple harmonic motion. So this is of this form. So simple harmonic motion. The circular motion of the ball in figure 1.1 has a diameter of 0.46 meter diameter. That distance there, 0.46 meter, and angular speed of 1.9 radian per second. For simple harmonic motion of shadow of the ball, figure 1.1, calculate the amplitude. Okay. So you find R. R is diameter divided by 2 is 0.23 meter. So that's the amplitude. Okay. Period is 2 pi over omega. That's omega. Maximum acceleration. Go to formula sheet if you've forgotten the formula. R omega square. R is 0.23. And then omega is omega. Okay. On figure 1.1, draw and label with a letter A the position of the shadow on the screen when the shadow has its maximum positive acceleration. Positive acceleration is this one, where it's going this way. Right? That one is going negative. Right? You want maximum. Maximum is at the end there. So it's A here. State two ways in which the first law of thermodynamics describes the internal energy of a system may be changed. Okay, want to try? Can? How do you change the internal energy according to the first law of thermodynamics? Right? That's the first law of thermodynamics. You can change it by either supply it with thermal energy or work done, no? Either work
Apply
done
or remove
or work done by it, no? So work
Oh
done
yeah.
by the system, thermal energy supplied to or removed from the system. Use the first law of thermodynamics to explain why a bicycle pump gets hot when it is used to pump up the tire velocity. Okay, do you want to try?
The process happens with like very fast, so no thermal energy is transferred to the system.
Okay, work done goes to increase the internal energy, no? Right? First, essentially, you do very fast. You pump your gas very fast, so no time for thermal energy to, to leave or enter the system. So no thermal energy is transferred to or from the system due to lack of time. Right? You do it very fast. When you pump air, work is done on gas to compress it. Internal energy increase, so temperature increase. So, right? 3 points, 3 marks. With reference to molecular energy, explain why the temperature of water remains at 100 degrees Celsius when it vaporizes in the kettle, even though it's being heated. Okay, you want to try? Can?
The kinetic energy of molecules remain constant during
Okay,
vaporization.
kinetic energy is constant or unchanged as temperature is unchanged. During vaporization, molecular separation increases. Heating causes potential energy of the molecule to increase. Okay, looks like less than 1 minute there. So enjoy your holiday before you come back again.
Right.
The following week we'll
Which
start
guys
it.
near teacher?
Okay, good night.
Right.
Anything you want to ask? Okay, if not, but good